talk of today, we look at something practical, which is kind of, I think if you were there for Frank's talk, network traffic analytics is something that's quite important and getting more important the more like cyber attacks we get and stuff like that, intrusions. And so I welcome Martin and Mirko from Cloudera to talk about that, how you would do that on Hadoop clusters. Thank you.
Thanks everyone, and thanks for staying for the last talk of this dev room. Let me, yeah, I think it's on, okay. It's green. Okay. So my colleague is Mirko and I'm Martin, and we both work for one of the Hadoop vendors, namely Cloudera. And we both work with customers. Solution architect basically means that we go on site with the customer and try to help them to learn Hadoop, to adopt Hadoop, and bring more and more workloads to Hadoop. And it's a very general question that we run into customers trying to ask for help to understand the system. That what does it mean that they are used to being maybe one monolithic application, or used to having a database system, and now this is this brave new world of Hadoop technologies where everything is distributed and your data is floating around in the cloud, and how do I make sense of that? So one of the ways to make sense of it is actually concentrate on the bottlenecks, and network traffic is very usually one of the bottlenecks of a Hadoop processing system. So we came up with a couple of ideas of how to visualize this for clients, and also to make sure that we ourselves understand these workloads better. So I will give you a little bit of the motivation of why, how Hadoop works and what we would like to visualize here. Then we go into the packet capturing and how we capture the data. We do a little bit of analytics with the Cloudera Hadoop stack, the CDH for short, and the Gephi toolkit, which is an open graph visualization platform, and produced the figure that you see on the side. So let's have a look at the network load of a Hadoop cluster, because we have hundreds, and in a couple of use cases, thousands of machines in one single cluster. Simple operations change. When you put a file onto a file system, that most of the time, because it's a distributed file system, DFS for short, includes some network operations. Usually these files can be so large that they are bigger than a hard disk in a single machine. Also, you want replication for fault tolerance. So just putting something to the file system is a network operation. Of course, getting something from the file system is also a network operation. Then you have to make sure that there is some service discovery, parts of the system know about each other, so you need some heartbeating going on in the system. As such, I would say a passive noise going on, still network traffic is being generated. And of course, data is not just sitting around in a cluster. You actually do some stuff on the data, transactions, analytics, you name it, again, generating traffic. And one of the not necessarily nice features that we discovered by trying to explain this to customers, if you look at the standard Hadoop monitoring tools today, the metrics that you can see for network utilization, they are aggregated on the host level, and a lot of times that doesn't give you the capability to look at individual services. So instead of I'm using 80% of the bandwidth, maybe I'm gonna say that, okay, my DFS is using 20%, my heartbeats are using 1%, and my processing jobs of these three workflows are using an additional 50%. Maybe that's what I would like to see in a setup like this. And currently, that's not what you necessarily get from these systems. Also, in this dev room today, you have heard about cybersecurity, and there's an Apache project that we are familiar with called Apache Spot, which is mostly pushed by Intel and Cloudera, but it's open source as is. It's an Apache project for intrusion detection. And we'll mention a little bit how we differ from their approach. So let's move to the data that we are using. We use standard packet capture data. So this is the library It's both implemented for Unix and Windows systems that you are familiar with if you use the tools built on top of it, TCP dump, Nmap, Wireshark, Snort, you name it. They all use this basic implementation. We used a Python hook for this, but it's the same data. A couple of gotchas in the data capturing. Of course, we don't want to create additional noise while capturing the data, so we capture it on the local machines and write it to local file system, and we only gather it after the capturing has finished. And we throw away the data in the packet itself. We are only capturing the structure of the graph. It's mostly for clustering and for visualization, not necessarily learning from the data inside the packet itself. On the contrary, what the Apache Spot guys focus on in terms of cyber security, they would like to learn topic analysis on the data itself inside the packets. One of their most important approaches include this, and they would like to build a cybersecurity platform for Hadoop using Hadoop technologies. Instead, we focus on the clustering and the visualization, as I've mentioned. So we had to come up with a couple of scenarios, and we examined 5 scenarios in detail, but here we only present 3 of those because those 3 were more important in terms of results. So we had a heavy batch workload called TerraSort, where we read input from the distributed file system, and we do a big distributed sort on the keys in this input, and would like to eventually write the output to the distributed file system again. We also captured the idle cluster, so have an idea of these background noise and heartbeats. And then we had a more interesting approach when we reached out to the Twitter streaming API with Spark streaming and collected data from the outside. And we wanted to see how that appears in a network like this. And also we wrote to HDFS. We could have written to Kafka or any other source of your choice. So the way currently it works, it's semi-automatic. We collect data in the Avrus format, for which you had the Avrus schema in 2 slides before, with this PKPy script. We transform the events into networks using Hive, which is a SQL API on top of Hadoop. Now we are migrating these workloads to Spark because then it's easier to register UDFs and makes our life easier. But currently it's in Hive. And also we use Giphy, this Open Graph visualization platform, to do the visualization layer. So let's have some initial results to give you some idea of what we have managed to capture. Both the size of the nodes and the width of the edges correspond to the workload. And in the TerraSort benchmark, what we have seen is the 5 nodes of our cluster were of course very prominent because we were reading data from the distributed file system, and the sorting also involves a big shuffle in between the nodes, so of course that communication had to be really prominent. But some other nodes were also included with just a little bit of traffic, and of course it's important to examine those. In the other case, we run the Twitter collection on just one single node, and of course that's the one in the center of this star schema. And that's the one that is of course also connected to the other 4 nodes that are in the cluster. However, it's connected to a lot of unknown new hosts that we haven't seen in the cluster yet. Those are the ones that are actually sending the Twitter data to our cluster. With that, I would like to pass the microphone to Mirko, who is going to go deeper with the analysis.
So, after looking into this very high-level initial results, we could see what we expected. We see two very typical different topologies of the communication networks. You see communication networks here on a host level, which is pretty interesting as a starting point, but what can we learn from here? Not much yet. Okay, there's a central node because one node speaks to the outside world and delivers data as an ingestion tool. We have an internal operation running on 5 nodes in parallel. Okay, that's cool. That's not something which helps us a lot. We have to look deeper. We have to increase the resolution. We must look into more details. This means we add port information, not only host information as we did in the very first analysis results. Next thing, we add a timestamp. We track the time-dependent graph, not as a snapshot for the whole period. We look into little time slices and make this whole thing more dynamic. And this allows us to do another thing. This allows us to connect to a time domain. This means we can switch between graph analytics and time series analytics. And in order to show something useful, Gephi will be our friend. Gephi allows us to collect data with time resolution, and Gephi plots and visualizes graphs with time resolution. You will see an example later. I mentioned to increase the resolution. We did it here. We added more details to the picture. What can we see? Not much at the moment. We see some clusters, some clouds of bubbles with the same color. Everything which is in the same color means here's a port available on a particular host. Via this port, some communication happened during our experiments. So we reconstruct first a static graph which only shows which ports and hosts have been involved during a certain data capture period. That's the first start. And now we must group the data a little bit, do a better layout, and do some statistics. First thing, in this cluster or in this graph now we have 1.5 thousand nodes, about 3,000 edges. And I realized that Gephi behaved not well anymore if this number goes up to 100,000, but capturing half an hour or an hour of data will explode the stuff. So we went to Spark and used Spark tools for analytics, but finally we do the whole visualization in Gephi. Our whole visualization means we start with a static network which represents our infrastructure. The colors here encode at the moment the hosts. Same color means ports on the same host. The black lines are our real communication channels. Whenever a package traveled from one port to another, it gives us such a trace. Okay, this looks good for the moment, but we can do more. We can now study the topology of this network. This communication network changes over time. So topological properties change over time. Very interesting. So different nodes become important. Depending on what measure we apply, we can now tune the things like we need. This is still a field where research has not delivered final answers yet. With Gephi and with Spark, we are able to calculate different topological properties. The interpretation is still an open problem. We don't go deeper here. Our goal is to track the whole system in a more specific way. Our initial question was how much of the network traffic is related to HDFS? How much is related to Spark, Shuffle and Sort or Shuffle services? And all these different questions arise if you want to tune the system. So this topology does not answer these questions, but we can see what hosts are very important and what are the dominant ports. Okay, that's an interesting aspect, but let's go away. Let's make this whole dynamic thing visible here. On the left-hand side, you see dynamically changing connectivity links between hosts. Okay, that's what we have seen. On the right-hand side, you see a different representation of the same data. It is now not grouped by host anymore. Such a color spanning area here, such a cluster in the same color, is now not a host, it's a subsystem. It's, for example, HBase, or it could be Zookeeper, or it could be MapReduce, or whatever. Depending on what software you deploy on your Hadoop cluster, you may end up with a very different setup of such clusters, and you don't usually not know what it is up front. We collect data without knowing that such clusters even exist. Our analysis procedure highlights this and finds them out automatically. So this is how we do it. We go from a host-centric representation to a layer or subsystem-centric representation. We turn things around. This means we track the graph over time. Now we apply such a component or cluster detection algorithm. And this cluster detection algorithm identifies such usually isolated clusters, because these subsystems are usually well isolated in a Hadoop system. Depending on your real environment, this could be different. Such clusters could be interconnected. In our case, they are not. So finally, if we have such clusters where the different ports can be on very different hosts, it makes sense to aggregate along these clusters, not along a host anymore. We aggregate now per subsystem and get some time series. And with this time series, we can say how much is the correlation between HDFS and HBase, or MapReduce and HDFS, and so on. This means if we change the perspective and aggregate along these new dimensions, we end up with time series, and we can look deeper into the behavior. A final remark here, this component-centric view is very helpful. It allows us to look again into the topology, but be careful. Absolute numbers in such a graph are really dangerous. These numbers here, this high degree or this huge circle, which is used here and here, they are totally misleading. You cannot conclude from this picture that these both are the most important ones. This is an artificial effect of the analysis procedure. Just as a warning, be careful with this. Always think about the right normalization. Usually you must look deeper into your data to get this. But such pictures help you in order to get central and decentral stuff by using a different layout algorithm. It depends all on your layout algorithm how these pictures look like. And if you want to cheat, you just have to change the algorithm for layouting. Depending on the layout, you can make the graph speaking. It's powerful, but also dangerous. You must be careful here again. We switch the domain. We go from graph to time series. What we see here is the overall activity during the MapReduce job and during the Twitter ingest job. Both jobs were running, and you see what we do inside the cluster has not much heavy traffic, but during data ingestion we record a lot of activity, but we don't know which subsystem is really causing this activity. This is why we group the stuff by subsystem, and we come up with one time series which represents the number of packets per time interval for each individual subsystem, starting with HDFS, where the name node is here just as an example used. We have the node manager, which organizes the workload in the cluster in red, and blue, black, and yellow are communications related to the job management system. So we can clearly separate this time series and see some effects. For Hadoop behavior analytics, you can figure out which kind of application has a lot of internal traffic and which not. And if you look in this picture here, we see in average the activity on the name node is much smaller. We have no blue, yellow or black one here. This means on this layer there is no activity going on. But what a surprise, this job is of the same type like these jobs. We can see here a result of system tuning. In the old ways, we have a lot of internal traffic. After tuning the system in a specific way, we could reduce this intermediate traffic and we could avoid the bottleneck. That's one result of using this method. So we are in the very first experiments. We have two at the moment. We have the idle cluster where only the background noise is visible. We have heavy ingest activity, and we can clearly see our method allows us to segregate this ingestion activity from all the background noise. So we can split multiple channels like you would do in an EEG, where you use frequency filtering during data collection. So we can observe that we have either one very active component, or we can see we have multiple competing components, multiple channels. Yeah, and all this depends on your algorithm. It depends on your workload. A normal ETL cluster would behave different than a graph processing cluster. But with this kind of measurement approach, we could measure the things, and then we have at least some benchmarks, and we can start tuning the stuff. So finally, we have to think what's coming next. First of all, we must improve the experiments. This means we have to run more experiments, we have to add more realistic workloads. For example, Flink streaming, Twitter Spark streaming is not done yet. Impala queries or even heavy H-based use cases, or even solar-based search use cases have not been tested yet, we will add all this to our agenda, to our scenario list, and then we come up with a different kind of visualization inspired by the talk in the morning where the Twitter real-time visualization was shown. We concluded, okay, it makes sense to have this for this measurement as well. So we can measure strange behavior or suspicious connections. And if we find such, if we have a classification for our traffic, then we could visualize it using Gephi as well. And Gephi, together with Spark, works here with our Gephi Hadoop connector. And then after we have settled this experiment platform a little bit better, we can do much more sophisticated analytics on top of the system. The goal is we want to learn more about the time series. We want to model the time series, but therefore we must first aggregate the data in the right way. And here we have shown our first experiments towards these results in the future. That's all for today. We have to say thanks to the audience and thanks to a bunch of colleagues which support the project in the background, which are not here. And that's all from my side. It's time for questions.
Any questions? One from here. Is this work open source? Is it
Yes, it is open source. It's not published yet. We have it still in an internal repository. We just clean it up. But yes, it is intended to be published soon.
Yeah, because I can imagine it's really useful also for other use cases, like for instance, Jörg at Mesos, if you look, like
Exactly.
communication between Mesos or DCOS nodes or something like that,
Right.
or other cloud infrastructure or something like that. So
Exactly. It's an experimentation and measurement thing, like an oscilloscope for IT guys.
Yeah, but in general, this subclustering by subsystem is done on a port level or on a port range level. Or
Currently, we do it without knowledge, and the result is overlapping with port ranges.
Okay.
So we can do port range statistics, and this is fuzzy matching with known port ranges, if you have such. If you know the configuration, then you can do this matching. Otherwise, we can just learn from the data.
Oh, cool.
That's really cool.
Open source, meaning we will be able to repeat kind of easily the same process?
Yeah.
That's the goal. We have the capturing project. It's a Python script. It still needs a little bit documentation to make you fast in doing the experiments and not wasting your time. That's our goal. And then we are thinking about contributing the stuff to the Apache Spot project. And finding the right structure and the right procedure and all the stuff. This is going on. We are not so fast so far yet. But yeah, that's the next thing
And also the analytic part is currently a little ad hoc. That's why we decided to converge towards Spark. So if you are new to these tools, then you only need to learn one tool, not learn three. Why do that? Yes, please.
Just go back to the component classification. You were doing that based on port ranges.
I could not really hear well. Could you please repeat?
The component level classification.
Yep.
You were just doing that by mapping it to known port ranges.
We can do a mapping to known port ranges in order to see which subsystem it is. If we have no information about it, we can do a good guess. And we can look into the pattern shown here. By looking into this pattern, into this one, and with a little bit knowledge about your algorithm and with some expectations, you can say which curve belongs to which subsystem. As a system engineer, you would probably be able to guess good. But let's say we have two jobs running in parallel, doing the same stuff from different users. Such a thing could not be isolated anymore by this algorithm. Here we need a little bit advanced information. Maybe we have to combine this approach with log information coming from Yarn. And if we have this integration, then we could hopefully isolate on a per application level. This would be a next step to isolate not per technical subsystem, but per application. Right now, we cannot do that.
Just was if you had PCAPs, if you gathered it from the actual payload of the network traffic, you can do it that way.
Yeah, that's a good question. If in the package there's enough information, because you have to have like a tag on each package to identify where it belongs to. And the raw network package content is not really that helpful, right? Because it's just partial information or
Yeah,
stuff like that.
So to reconstruct the application level, you need both the packet data and the yarn resource manager logs, because that's going to tell you that this application has these ports on these machines, and then you join that together, then you can construct the graph.
When you have tuned some Hadoop cluster that was acting up, what do you find the most? You need to tune the network, the job, or the Caldera subsystem?
Do you want to explain? Okay. For this example here, we did one thing. We increased the replication level of the data. Instead of having 3 replica, we have now 5, 1 per host. In a 100-node cluster, this would be overwhelming. But for our example, if we bring maximum data locality into the play, the network drops. It's an academic example here, just for showing the effect, or even just to figure out if the effect is visible. And the result is yes. But in order to do a better quantitative analysis, we need to figure out what resolution is the best. We don't have this yet. So depending on time resolution, your results could vary. So that's also a problem we have to deal with.
So of course this is most useful for jobs that are network bounded anyway. So you wouldn't see much of an effect if you had a memory bounded job and then you added more memory. So that's how far you get with such an approach.
We are interested in looking into graphics to see how it works when the nodes communicate with each other on a graph level and not on a server level. Maybe we can also help to tune the graph algorithm for itself, because such a graph algorithm is heavy network bound. And then we can say, okay, this could be a helpful tool. We will see how it works out.
What about the overhead of this kind of monitoring? Because you use pickups, so it is raw data and transfer, not you are not analyzing flows, right? Metadata about communication.
Yeah, so we capture it on the hosts, and these jobs weren't really CPU bound, so the only part it's captured on each individual host, so we are not introducing any new overhead to the network itself that we are trying to capture. That was the basic setup that we try to avoid. Of course, we shouldn't introduce any overhead, possibly if we can. You can adjust this in pickup the way you want to sample. Currently we try to capture as much data as we could to capture the most of the network, but if you find that that overhead is just huge, then PickUpI has an option to only capture one data packet in 100 or 1,000, so you can go in that direction.
And you could have also like a window based that you say, okay, I just capture how many bytes per second go on this port, and when does it start and when does it end, and then you have like a volume data capture kind of, which kind of summarizes, and then you kind of choose the time range, if what it per second per 5 seconds or something like that, and then it would give you enough information about the communication flows, but you don't need the raw data because you actually want to know when did it start, when did it end, and how much data went over the connection.
Yeah.
Cool. Any other questions? Otherwise, thanks a lot for the talk. It was really, really interesting. Before you leave, I want to use the opportunity to thank you all for coming, for attending all these talks. I hope you got something out of it. For me, it was quite interesting. There's a feedback mechanism on the FOSDEM website, so if you have any feedback to any of the talks for the presenters, or also for us, then please don't hesitate to give feedback. And otherwise, have a good evening and a good day tomorrow. And